Okay, let's get right into it. What if I told you that you could take an entire complicated data structure, I'm talking about a binary tree, and just squish it down into a single line of text, and then, from that one line, rebuild it perfectly every single time? Well, that's exactly what we're going to master today. And trust me, this is one of those classic coding interview questions you really want to know.
So here's the puzzle we're trying to solve. You've got this tree living in your computer's memory. How do you basically write down a blueprint for it? A set of instructions so precise that anyone, or any other computer, could build the exact same tree just by reading your notes.
This whole process has a name, and it's called serialization. And honestly, the best way to get it is to forget about code for a second. Imagine you're describing your family tree to a friend over the phone. You can't just list off names, right? You have to explain who's connected to whom. Serialization is creating that perfect, unambiguous recipe so they can draw it out flawlessly on their end.
So let's really dig into the what and the why here, because this isn't just some abstract puzzle for interviews. This concept is literally the backbone of countless systems that we all use every single day.
Yeah, this is why it matters. Every time an application saves its state, or an API sends you a chunk of data, or a big system needs to take a snapshot for a cache, that's serialization at work. It's the magic that lets us move complex data out of active memory and into a format that we can actually save or send across a network. So, how do we actually write this recipe? There are a few ways to go about it, but we're going to focus on one that is just beautifully simple and super effective, the pre-order traversal method. This is our game plan, our strategy for walking through the tree and taking notes.
The rules are incredibly straightforward. For any node you're on, first you write down its value. Simple. Then you go explore its entire left side. Once that's all done, you come back and explore the entire right side. But, and this is the absolute key, the secret sauce, if a child is missing, you have to make a note of it. We'll use a special marker, like a hash symbol, to represent null. Without this one little detail, our whole recipe falls apart.
All right, let's get our hands dirty and actually walk through an example. We always start at the root. Rule number 1, record its value. So our string kicks off with 1.
Now, Rule 2 tells us to head down the left subtree. We land on node 2, and we record its value. Our string is now 1, 2.
Okay, now for that crucial rule. We look at node 2. Does it have a left child? Nope. So we record our null marker, hashtag. Does it have a right child? Nope again. So we add another hashtag. And just like that, the entire little world of node 2 is perfectly described.
Since we've finished the entire left side of the root, we pop back up. Rule 3 says it's time to check out the right side. So we head over to node 3 and, you guessed it, we record its value.
And the pattern just keeps going. From node 3, we go left to node 4, write down its value, and then add 2 null markers for its 2 missing children.
We're almost there. We pop back up to node 3 one last time to explore its right side. We find 5, record it, and then add its 2 null children. And that's it. Our recipe is complete. We've captured every node, and just as importantly, every single empty spot.
You know, what makes this so elegant is that rebuilding the tree, the deserialization part, is just following the recipe. You read the string, one piece at a time. If you see a number, you create a new node, and then you start building out its children. If you see a null marker, that's your signal to stop. That branch is empty. You just return. It's that simple.
And check this out. This method has a really cool mathematical property. For any tree with n nodes, this specific way of doing things will always give you exactly 2 n plus 1 tokens. It's n tokens for the nodes themselves and n plus 1 tokens for all those nulls. Dropping a little gem like that in an interview, well, that shows you're not just coding, you're really understanding what's going on underneath.
Okay, so we've totally got the logic down. Now let's chat about how this actually turns into code without getting totally bogged down in every single line. So you're basically going to have 2 functions that are perfect mirror images of each other. The serialize function is your writer. It's the one that walks the tree using that pre-order traversal and builds up the string. Then you have the deserialize function. It's your reader. It takes that string, breaks it into pieces, and follows the recipe to build the tree back up. Now for the part that really separates a good interview answer from a great one, performance analysis. We have a working solution, but is it any good? How fast is it? How much memory does it eat up?
Let's break it down. Time complexity is linear, or O of n, which is great. That's because we touch each node and process each token just one time, no wasted work. The overall space for our final string is also O of n, which makes sense. But here's the detail an interviewer is listening for: auxiliary space. That's the extra memory we use during the process. With our recursive solution, that's the call stack, and it only grows as deep as the tree is tall, which we call h.
Hey, before you rush off to code this, let's talk about a few common traps. Seriously, the #1 mistake people make is forgetting the null markers. Without them, your recipe is ambiguous and basically useless. Also, don't forget that recursion isn't a magic bullet. If you get a super deep, skewed tree, you could actually blow the stack. And finally, always be ready to handle bad input. Make sure your deserializer doesn't crash if it gets a weird string. Okay, let's put it all together. You're in the hot seat. How did you present all this knowledge to absolutely crush this question in an interview?
A top-tier engineer always talks about trade-offs. You should be ready to compare our depth-first approach, that's the pre-order we used, with another popular method like breadth-first search. The key difference to highlight is that auxiliary space. Our DFS took O of h space for the tree's height. A BFS approach would use a Q taking O of w space for the tree's maximum width. Knowing when one is better than the other, like for a tall, skinny tree versus a short, wide one, that's a huge plus.
So here's your cheat sheet. These are your talking points. Start strong by stating your invariants, like that 2n plus 1 token count. Justify your ON time complexity cleanly. Dive right into the space trade-offs we just talked about. And finally, show you've thought about the weird stuff by mentioning edge cases, like what happens with an empty tree or a completely lopsided one.
So, the bottom line is this. You now have a solid, efficient, and really elegant method for this classic problem. The pre-order traversal with null markers is a powerhouse technique. It gives you a correct and confident solution every single time.
But that brings us to one last, more advanced question. We'll leave you with this little challenge. A binary search tree has that special ordering property, right? Left is smaller, right is bigger. Given that extra piece of information, do you still need all those null markers? How could you make the recipe even smaller, even more compact? If you can figure that out, you're well on your way to true mastery.